is about discrete mass parameter system, and it is required to find effective mass at point A, which is moving with X. So all the kinetic energies has to be obtained and to be summed all. That will be the total kinetic energy. And then this is the first step. And using, because of the rigid body involved here, which is the rocker arm, all the points on the rocker arm are related. And then we can get the relationship of the points, like point A and point B are related if we draw a similar triangle. Also, theta and X at A or XP, it is called, is related. They are related, and also XB and theta are related. So after we write all the kinetic energies, and then we can sum them up, and then replace the other quantities in terms of the required point X. And then we make it in term, we rewrite it as kinetic energy equal to 1/2 M effective times X dot squared. Okay, the same thing with the question number 2 and number 3. Number 4, it is about a cantilever beam. Then you have to assume a deflection shape. Already it is mentioned that we have to use the deflection of a cantilever beam at under concentrated mass, under concentrated force at endpoint, which is at X equal to L. Okay, the deflection, you can find this by from the deflection equation, d square y by dx squared equal to m over ei. Okay, or you can find it from one of the textbooks. Okay, so and then you use y, and you use the function of x only. You don't need the exact deflection under concentrated force. You need the distribution shape of the deflection of the beam. Okay, so I will start the next section, which is about viscously damped system. Okay, just for those who are online, just hold on a second. Let me print out those slides. Okay, so this is the chapter. We finished up to at this point. This is slide. So from slide 31, print up to 36. Okay, so this is the about viscously damped system in which there is, damping. This type of damping, we call it viscous, and we talked about, viscous damping in chapter 1 as introduction, that the force is directly proportional with the velocity in the viscous damper. There are other types of damping, but we will start with viscous damping. Because that can be controllable, because the relationship between the force in the damper is directly proportional with the velocity, okay, which is x dot. So you can have, and the constant of proportionality is c. So you can control the value or change the value of c to get the required damping. Okay. So if c equal to 0, this is undamped, and you will see that there are 3 different values of c, and we will obtain a parameter that will determine the behavior of oscillation of the system. For undamped system, the oscillation is continuously, because it is an ideal. Once the system starts to oscillate after initial disturbance, it will continue to oscillate with the same amplitude. That amplitude will be always the same for each cycle. Okay, the amplitude is, this is, if you draw, this is a 0 line, this is the amplitude. There will be no changes in this amplitude A for all cycles, you know. So we can, if you start, this is the starting of the first cycle. This is the end of the first cycle, but it is the start of the second cycle. But you will see that amplitude at each cycle, at the beginning of each cycle is the same. This is for undamped when c equal to 0. Okay, but for damped system, the amplitude will decay, which means the amplitude at the beginning of each cycle, it will be decreasing with time. So we will talk about the values of the dimensionless parameter that determines the behavior of oscillation. Okay, so it is the other types of damping will be friction, hysteresis, internal damping of materials, which you know, air resistance, drag forces. Those are also reduces the amplitude of vibration with time. Okay, but this one you can control it. You can add this device to control the vibration or to decrease the vibration at the required manner, yani behavior of the oscillations. You can let the vibration decay very quickly or decay slowly or decay with oscillation or decay without oscillation, all from this device, okay, which you can see in the, it is part of the shock absorber of the suspension in the automobiles, which is a spring and damper, the shock absorber. So it is a cylinder with piston inside, and piston has holes and oil. If the piston moves relative to the cylinder, there will be resistance to the velocity. Okay, so it is added here as you see in the diagram in parallel with the spring. Okay, and in parallel because they have the velocity and the displacement are the same for both elements, the spring and the damper and the mass. At equilibrium, which is the next figure. Yeah. اي هذا هو. اي يعني يسمونه شوك ابزوربر ونفس الجانبي. يعني consists of a spring, a coil. Inside it there is the viscous damper. Okay, so at equilibrium, the damper is not active because it is related to velocity. And if the car is not bouncing up and down, the only element carries the weight of the car is the spring, not the damper. The damper will be active if there is vibration up and down. Okay, so it does not carry static weight. So in equilibrium, we have only the spring force, which is same as the undamped system. And the free diagram will be the spring force K delta and the weight. Delta is the statical deflection as we mentioned before. So K delta minus W equal to 0 for equilibrium. And this is the vibration, the free body diagram for arbitrary position. The weight is removed because of this equation, because we use the fact that the weight equal to K delta, so it is removed from the second free body diagram. You don't see the weight here. And you can do the same thing for any problem that is supported vertically against gravity, that the weight will be removed from static equilibrium. So it is Cx dot, Kx is the spring force from Hooke's law. Cx dot is the force of the damper. The relation is linear, as I said, and C is the constant of proportionality, and it is called damping coefficient. Okay, C is the damping coefficient or the constant. The unit of C is Newton meter per meter per second. Okay, which is written as Newton second per meter. Okay, and for the second free body diagram, you use Newton second law, sum of forces equal to mx double dot. The positive direction is downward, and then the forces are upward, kx and cx that are negative. And if you have a force, then it is in the positive direction. So after applying the Newton second law, we will get mx double dot plus cx dot plus kx equal to f of t. If f of t is 0, this will be the free vibration. If the f of t is not 0, then it is a forced vibration. So since we are in chapter 2, which is about the free vibration, we will put f of t equal to 0 to study the characteristics and the behavior of the oscillations of the system under free vibration. So f of t is 0, then becomes the equation mx double dot plus cx dot plus kx equal to 0. The solution for this differential equation, we will do it now, but we will use the solution again. Yani we will not solve differential equation again and again because it is the same. There will be no changes. This is always mx double dot plus cx dot plus kx equal to 0 or equal to f of t, and c is either 0 or constant or other values, and either 0 or other positive values. Okay, so the approach is to assume exponential solution x equal to e to power st and substitute in the differential equation. So when you substitute in the differential equation, you get e to power x equal to e to power st, then x dot is s e to power st, and x double dot is s squared e to power st. So when you substitute in the differential equation, it is m s squared times e to power st plus c times s plus k, all multiplied by e to power st equal to 0. Okay, e to power st is not 0, so the parentheses between parentheses is equal to 0. We have ms squared plus cs plus k equal to 0. Okay, this equation is called the characteristic equation. Okay, the characteristic equation from which you can find the values of s. S is a constant, and expected value for s are 2. There are 2 values for s, but because the differential equation is second order, ordinary differential equation, so there should be 2 values for s. And obtain from the characteristic equation after we did the substitution. So ms squared plus cs plus k times e to power st. So we put the terms in the parentheses equal to 0 because e to power st is not 0. And then dividing by m, we get s squared plus c over ms plus k over m equal to 0, which is, this is the characteristic equation. The roots, we use the general equation to find the roots of this equation. This is a quadratic equation in S. And there will be 2 values, S1 and S2 will be minus C over 2M plus minus square root of C over 2M squared minus K over M. Okay. So it means that we have, depending on the values, we have S1 and S2. Then we substitute, since there are two values for S1, the total solution will be the summation of the two solutions. So this is called first solution, and this is called second solution. First solution, second solution, because there are two, and both are satisfying the differential equation. It means both are solution, and then should be added. A is and B are constants to be found for the initial conditions. So A times e to power S1t plus B times e to power S2t, A and B to be evaluated from initial conditions, which are x at 0 and x dot at 0, which is the initial displacement and initial velocity. Okay. When you substitute for both solutions or both values of S1 and S2, you will have A e to power S1. We take S1 the smallest value. So there is S1 and S2. There is plus minus, right? So we take, since there is a minus here, we take the plus will give us the smallest value. Okay, so e to power minus c over 2m plus the square root c over 2m squared minus k over m multiplied by t plus b times e to power minus c over 2m minus the square root of c over 2m squared minus k over m. That هتنسوي؟ Okay, the plus minus because of the roots. Okay, and the roots are, there's a plus minus, we use the general equation. So we take the plus is going to give us the smallest root. Okay, so there's addition, it doesn't matter we use, this is the first or this is the first, doesn't matter. Now what you can see, if you take, distribute the t inside the bracket, you can take e to power minus c over 2m as a common factor times t as a common factor. And this will be a times e to power the square root of c over 2m squared minus k over m multiplied by t plus b e to power minus square root of c over 2m squared minus k over m times t. And we close the square bracket. Okay, which is shown here. That is this is the function that we take it as a common function, multiply by addition by two functions in parentheses. This is an exponential function. When you plot e to power minus c over 2m, starting with t equal to 0, okay, if t equal to 0, this is starting from 1. And then when t progresses, and time progresses, this will decay and become asymptotic to t-axis. Okay, this give us an idea that whatever the behavior of the two functions inside the parentheses, the amplitude will be decaying always if c is not 0. Okay, if the value of c is not 0. Okay, and this is the function that is responsible for reducing the amplitude with time, for if the value of c is not 0, and it's called exponentially decaying function. So the two functions in the parentheses are multiplied by an exponentially decaying function. So it is forcing the amplitude to go to 0. So if the c is 0, it means this will not be decaying. It will be always the same, of the same amplitude. The behavior of the oscillations are determined from the square root, the radical of the square root, the value inside the square root. C over 2m squared minus k over m. You know, because of the minus in between the two, this is a minus here, minus, right? There are three possibilities. If this is a plus, there is only one possibility. But because it is minus here, there are three possibilities. The term, the value, the terms in the square root, which is called the radical, can be positive or negative or zero because of the subtraction. Okay, so if it is positive, it means that c over 2m squared is greater than k over m. Okay, if it is positive, if you have an exponential function with a positive power, I mean real, you know, this is when the value of the radical is positive, the square root of a positive value or number is a real number, right? It's not square root of minus something, it is square root of a positive value, then it is a real number. And exponential function, a real, when we plot a function that is exponential with real, it is with t equal to 0, either increasing if the power is positive, which is e to power, let's say, the square root of c over 2m squared minus k over m times t. So it is starting from 1, but it is increasing to infinity if it is open. And the other one is with the negative square root, I mean with the negative exponent. This is positive. Okay, inside the square root it is positive, but there could be minus or a plus outside. So it is real, exponents are real, the roots S1 and S2 are real, and we get non-oscillatory oscillations, right? Because you are multiplying exponential function by another exponential function. The result will be an exponential function. Okay, so it means there is no oscillations here. In this case, this damping is called overdamped. The value of C here is high. If this is the case, it is called overdamped. And overdamped, it means there is no oscillation, and the value of C is preventing the system from oscillation. So if you give an initial condition to, if you take the spring mass system, and this is the equilibrium position, this is K and C, and this is M. If you give initial condition, let's say you push this downward, okay, and then release. This is giving initial 0, initial displacement is positive, greater than 0. Let's say that x dot as 0 is 0, as an example, yani. Then this will go backward, will go up. I mean, the mass will go up to equilibrium position. But it will take time to reach the equilibrium without exceeding the equilibrium position. There will be no oscillations. So this will be at final time. This will go back to the oscillation, back to the equilibrium. This is the equilibrium position. Without exceeding the equilibrium. So if you plot the x versus t, and you give initial position, initial displacement positive, okay, this will decay. This way, it will decay. Okay, without oscillations. And this is the overdamped case. The other case, which is when the radical is negative, we can use here Euler equation, because a square root of a negative value will give us imaginary number. And imaginary number will be that contains square root of -1. So you can write, we have the radical is c over 2m square minus k over m. If this is negative, you can switch them and take a square root of -1 as a common factor. So the radical becomes I square root of k over m instead of c over m squared, k over m minus c over 2m squared. And if you have e to power this, this is the exponent of the exponential function. This will reduces to sine and cosine. So this will be cosine of the square root, this is multiplied by t, k over m minus c over 2m squared times t plus minus I sine square root of k over m minus c over 2m squared times t. Okay, so this is using Euler equation. The exponential functions between the parentheses are reducing to sine and cosine terms. So each exponential function inside the parentheses, this will give you sine and cosine term, and this will give you sine and cosine term. Then you can add the sine terms together and the cosine terms together. So instead of having a constant a and b, this will be just a new constant c and d, for example. So the result will be x equal to the same exponential function outside, which is minus c over 2m times t, multiplied by c times, you can say this is sine of the square root of k over m minus c over 2m times t plus d. I is just a constant. So I multiply by a or multiply by b, that will give you maybe real. So c and d are just a constant. So this will be cosine of the square root of k over m minus c over 2m squared multiplied by t. And since the two terms inside the parentheses were reduced to sine and cosine, which are oscillatory functions. Okay, and this case occurs when the value of C is relatively small, and this case is called underdamped, which is allowing to have oscillations. Oscillations, as it was the case for undamped, but the amplitude will be decaying because of the exponentially decaying functions taken as multiplied by the whole, by the the two terms. So this will result into an oscillator. If you give initial disturbance positive, then it will oscillate with decaying amplitude. So if this is A1 and this is A2 and this is A3, okay, A3, A1 is greater than A2, greater than A3, and so on. So that means the amplitude is decaying, and it is decaying exponentially because the function that is forcing the amplitude to decay is an exponential function. So it is going to decay exponentially this way. Yeah. الفرق ما بينهم, we will find the difference between them. We will find it. Okay, and that will depend on how much is the value of C. Okay, so this is called underdamped. So there is overdamped, which means no oscillations are allowed, and under them there will be oscillations. And we have the case when it is 0, which is the limiting case, C over 2m squared minus K over m equal to 0. This is called limiting case, which is between overdamped and underdamped, or between oscillatory and non-oscillatory. So just if this is a little greater than 0, it is overdamped. If it is just a little less than 0, it is underdamped. So it is the limiting case. And this is called the critical damping. Critical does not mean dangerous. It just means the transition. This is the transition case. And we call this value of C that give you critical damping CC. Okay, this is called the critical damping coefficient. And can be obtained by, since this is equal to 0, you can put C over 2m squared equal to K over m. And then we call this value of CC, and then you can take square root and get the value of CC equal to 2m square root of K over m. And K over m, we know it is omega m for the spring mass system. Okay, so this is omega m. So it is 2m omega n, or you take m inside the square root, you will get 2 square root of km. This is the value of CC. So now you can see that to know there are 3 systems now here. Although the system consists of a spring mass and damper, but depending on the value of C, you will get 3 different types of system. If you include C equal to 0, you have 4 types of systems. And for each one, the equation of the response, which is the solution, will be different. Okay, as you saw in the overdamped, the equation will be as is given here, without any reduction, without any modification. If you have the underdamped, the equations is now with sine and cosine, not exponential functions. And if it is for critically damped, when it is a critically damped, as you can see, C over 2m squared minus K over m equal to 0, then S1 and S2 are equal. There are double roots here. And then if you go back to the solution, this is when the radicals are 0, then there is no need to have A plus B anymore. This is just one constant, because A multiplied by 1 plus B multiplied by 1. So this is just one constant, and this is one solution. And this occurs when we have the roots are repeated or double root. Then the solution will be also, the response will be different. We have to multiply the first solution multiplied by t to get the second solution, as you will do for any differential equation if you have a repeated roots. Okay, so the equation, this is for underdamped. For critically damped, this will be e to power minus c over 2mt multiplied by a plus b times t. Okay, so you can change this to c and d, just to give you an idea that those constants are not the same as a and d. So there are 3 equations here. The first equation above here is for overdamped. It is valid for overdamped, but not valid for all the cases. For underdamped, it will contain sine and cosine. For critically damped, it will be something like this: c plus d times t, multiplied by the exponential function e to the power minus c over 2mt. Now, to determine which one is which type of the system we have, we compare with CC. And the value of C, this is obtained. You can see this is CC is not given. It's not the value of C of the damper. This is not the value of C of the damper. This is part of the system. It's like omega n. K and m are given, but omega n is square root of K over m. Okay, the same thing here. There is the system has a parameter called critical damping coefficient. As it has omega n. It is characteristic of a system which is nature frequency. If you change the system, it means you change K and M, then you change the omega n. Omega n is constant for a given system. Cc is also constant for a given system, which is obtained from this equation, 2m omega n, or 2 square root of Km. Okay, so this is not the value of C. Now to check whether the system you have is underdamped, overdamped, or critically damped, you compare with the system system parameter, which is Cc. Then the way to compare is by taking the ratio, and it's called damping ratio or damping factor. And this is called, this is a Greek letter zeta. I don't know, they are different here in shape, but it is zeta. Huh? There are different zetas in Greek letters. There is capital letter, small letter as well. So zeta is C over Cc, which is the ratio of the given value of C of the damper as divided by the critical damping coefficient of the system. And then you can use this as, this is a dimensionless parameter now, because the value you are dividing C over Cc, they have both quantities have the same units. So it will be dimensionless parameter. You can write the two roots in terms of zeta as well. Okay, and that will give you a clear picture of how is the oscillation is going to be. We have in the roots C over 2m. So you can multiply C over 2m by Cc and divide by Cc. And C over Cc is zeta. And this Cc is equal to 2m omega n. Okay, you keep one of the one in the denominator, so that C over Cc is zeta, and you substitute for the Cc, which is 2m omega n, to cancel out m and m, 2 and 2. Okay, and this will be equal to 2 zeta omega n. 2 zeta omega n. And the roots, okay, the roots, there is C over 2m, C over 2m here. So you can replace those two with 2 zeta omega n, 2 zeta omega n, and also K over m is what? Is omega n squared, right? So this will be omega n squared inside, and this will be whole thing squared. Then you can reduce, instead of having 3 parameters, C, K, and M, you will have only 2 parameters. So this will reduce, the roots will reduce, S1 and S2 will reduce to minus zeta. You can take omega n as a common factor, minus zeta plus minus square root of zeta square minus 1. And as you can see, instead of finding C and dividing by Cc, you can determine this that the roots are real, which will lead to overdamped, or they are imaginary, which will lead to underdamped, or repeated, all from zeta. So if zeta is less than 1, it means this is positive. It is underdamped. Okay. If zeta is greater than 1, this value is positive, which means overdamped. If zeta equal to 1, this is repeated, which means critically damped. So now we can determine the 3 cases, which are, in summary, can be compared with zeta. If zeta is less than 1, the system is underdamped. If zeta greater than 1, this is overdamped. And you know what happens if it is underdamped or overdamped. Oscillations for underdamped, no oscillations for the overdamp. And if zeta equal to 1, it means critically damped. And also the differential equation can be written in terms of these two parameters. We have m x double dot plus c x dot plus kx equal to f of t, or equal to 0 for m dot, for free vibration. If we divide by m, we get x double dot plus c over m x dot plus k over m x equal to 0. Okay, so x double dot plus c over m is I think I did here. There is no 2 here, right? 2 and 2 cancel. This 2 will cancel out. Okay, so this will be only zeta omega n. Okay, so here somewhere I wrote, yeah, this is zeta omega n only. In the differential equation, this will be c over m, which is 2 zeta omega n. Plus k over m is omega n squared x equal to 0. So from the differential equation, you can determine two things, two parameters, omega n and zeta. Okay, so as an example, for the last minute here, let's say 2x double dot plus 50x dot plus 500 x equal to 0. When you divide by 2, you get x double dot plus 25x dot plus 250x equal to 0. Therefore, omega n from here is square root of 250, and 2 zeta omega n equal to 25. You need to make this coefficient equal to 1, unity. And you can find omega n and zeta. Okay, any questions? Yeah. It's critical damping. If C equal to CC, we call the system is oscillating with the critical damping. known property. It can be calculated. As we calculate omega n of the system, we can calculate CC for the system. Okay, and if C equal to CC, then it is a critically damped. Okay, so we can determine this from the damping factor Z. Okay, so there is one more slide. We will finish this next time, and we'll see you next lecture, inshallah.